All right, so continuing with section 11.3, we're going to look at a bunch of examples of data distributions so we can get a grip on some different examples, figure out what things are skewed, what things aren't. So the first one we have here is the distribution of shoe sizes of UK men. And this is something that you would find very consistent across the world, is something like the distribution of shoe sizes is going to follow a symmetric distribution. So this one is pretty obviously symmetric. It doesn't look significantly skewed one way or another. On the bottom here, we have the shoe size, and on the right side, we have their percentage of the total. And as you can see, 8.5 is listed as being what looks like 15% of all results. And on each side, we have 9 at 14%, and at 13%, 8, 11% for 7.5, 12% for 9.5. I think you might be able to say this is slightly skewed in one direction or the other, but overall, it's a pretty symmetric distribution. And you'll typically find this in stuff like height, shoe size, which is correlated with height. There's a variety of natural phenomena which lend themselves to a normal distribution. But height, I think, is one of the most obvious examples that you'll see pretty frequently. And in fact, we will show height later in one of our examples when we look at a special type of distribution we haven't talked a ton about yet. So for the symmetric distribution here, we would use the mean and the standard deviation to represent the data set in terms of center and spread. The median, mode, and mean of a symmetric distribution like this are all going to be pretty much the same. So we'd expect all of them to be at or around 8.5 there, since it's the highest data point. Now, if we go ahead and we look at our next piece of data, our next graph, this is the men's long jump qualifying round results. As you can tell, the skew is already given in this particular example as being negative 1.12, meaning that we have a negative skew, aka it's skewed to the left. So as you can see here, we have a number of pieces of data, and the density essentially represents how frequently something appears. So the higher the density, the more frequently it happened. So it's the best jump on 3 attempts. And as you can see here, the distance is there's a lot of data right around the peak here. But then there's this incredibly long tail that goes down this way, which causes it to be skewed to the left. And for this left skew or negative skew, we would want to use the median instead of the mean to represent the data set. And we would instead use the 5-number summary rather than the standard deviation. And just as a quick demonstration, in a data set like this, we would expect the following to occur. This first line I drew, the tallest line, this is where the mode is. Obviously, it's the peak of the graph, so the mode is right here. The next one would be where we'd expect the median to be, or the middle point of the data set. And the third line, the furthest to the left, is where we would expect our mean to be. This is, again, why we use our median instead of our mean on this one. The mean does not do as good of a job of representing the data set because it's so heavily influenced by the tail. And the median is pretty close to the mode, and it overall represents a large portion of the data and gives you a much better idea of where the data is. Of course, that's why we ultimately have to use the 5-number summary, because the standard deviation doesn't provide much useful information for us. All right, let's look at another data set. This is yearly income with relatively frequency on the left side. As you can see, this one is pretty clearly positively skewed. And I think we've already talked about this in one of the videos, but yearly income is one of the things that's really clearly skewed to the right, because there are some people who just make tons and tons and tons and tons of money, whereas the reality is most of us are going to be somewhere in here. And again, this is another example where we have a mode over here. The median will be somewhere right here. I probably should have done that in a little bit more obvious of a color. put it in green. And then the mean is going to be somewhere over here because of how incredibly skewed the data is. So this is another great example. We want to use the median to represent the data because that tells us a much better idea of where everyone is rather than the mode, which would tell us everyone is poor, and the mean, which is incredibly badly skewed by a handful of high earners. All right, so on this next one, I'm going to pull it up. And you might want to spend a moment and think about, maybe pause the video and ask yourself, all right, is this left skewed, right skewed, symmetric? What are you thinking about it? All right, this set of data is pretty clearly left skewed because we have these two peaks on the right side, and then we have the skew off to the left. This is looking at the age of death in the United States in 1950 and in 2015. So as you can see here, Americans have been living longer, and infant mortality, which is represented by this bump over here, has gone down significantly since the 1950s. And the average age of death has gone up slightly, and the median age has also gone up, as well as the mode. But once again, the long tail gives it away. This is skewed to the left. The mean is, of course, lower than the mode, and the median, which is not listed on this, would be between the two of them. And that pretty much tells the story right there. So this is, again, very similar to one of the distributions we've already seen. It is heavily, heavily, heavily skewed towards the left by all these people who end up, unfortunately, dying pretty young. All right, let's take a look at another example. And this sort of serves as a twofold example. So this is actually two graphs superimposed on one another. The left one is the height of women, or the yellow one is the height of women, and the green one is the height of men. And if you were just looking at this data set and asking yourself, all right, and you weren't delineating between men and women, it would look like this was actually a bimodal distribution. But what we in fact have is just two sets of data which are being graphed on the same series of graphs, on the same axes. And this is something that will happen sometimes if you end up with like a bimodal distribution of data. It's not really that you actually have a bimodal distribution of data. Frequently what it means is you have two different sets of data that actually need to be separated out. But within each of these two sets of data, can you say what type of distribution this is? You might want to pause and think about it. I'm hoping that you'll say that it's relatively obvious, and considering what I've said earlier in the video, it's relatively obvious that each of these are a symmetric distribution. Men and women tend to have a normal or symmetric distribution around whatever their average height is. For men, it looks like that average height is like 69 inches, maybe 68 and a half. That's around 5'9". And for women, it looks like it's closer to 63 inches. So that would be 5'3". And obviously this, if we knew what our standard deviation was, it would tell us a tremendous amount about where 68 and 95% of the data is. It looks like it's something for women like this. It probably looks like 95% of women are between 58 and 68 inches tall, or 69 inches tall, something like that. All right, now let's take a look at another set of data. This is the distribution of home sale prices in Suffolk County, Massachusetts, comparing 2007 and 2017. And you might want to take a moment to think about how this data is skewed, although I think it should be pretty obvious to tell that it is skewed to the right, because we have these two massive peaks in 2007 and a smaller peak in 2017. And then there is a huge long tail that goes off towards the right as the prices go up. Prices tend to be something that is usually skewed to the right because And here's something I always say, you can buy something for whatever amount of money you want to pay for it. So when it comes to houses, there are many luxury homes, an increasing number of luxury homes, as you can see from the 2017 data to the 2007 data. But you can basically pay any amount of money for something that you want, as long as you get above whatever the minimum might be. And in this example, this is obviously skewed heavily towards the right, as you can see by the number of 2 million, 1.5, $1 million homes. You can pretty easily identify the modes as being the peak of the graphs, and then the mean would be skewed to the right relative to our mode. Once again, this is also known as a positive skew. All right, finally, we have one more distribution of data and a brief social studies lesson. And this is from the Pew Research Center, and I guess I got it off of the Economist website, but this refers to the political party attitudes of Democrats and Republicans since 1994, with snapshots in 2004 and 2017. So as you can see, the Democratic and Republican Party were quite close to each other, and there's actually an enormous number of overlap between the two parties in 1994 and 2004. As you can see, there was very little difference between a consistent conservative, or between the median conservative or the median Republican and the median Democrat in 1994 and 2004. It wasn't even appropriate to label the parties really liberal and conservative, considering how similar their voter profiles looked at this time. In 2017, obviously, the data looks more like a bimodal distribution than a normal distribution. I mean, it was technically still bimodal before, but it was much closer to being a normal distribution. But in 2017, it looks much more like a bimodal distribution, as you can see how significantly left the Democrats have moved, and the significant amount the Republicans have moved to the right. But once again, if these two graphs were not colored as being blue and red, you might be mistaken in believing that this actually represents a bimodal distribution, when in reality what's happening here is we simply have two different sets of data being superimposed on the same graph. One representing the liberalness of Democrats and the liberalness or conservativeness of Democrats, and the other representing the conservativeness or liberalness of Republicans. So that is a variety of different types of graphs looking at their symmetry or skew, as well as a couple of these crazy, seemingly bimodal distributions.